Let's look at the half waveform, half wave symmetry, and we see ft has half wave symmetry if ft is equal negative ft plus or minus t over 2. Right. So this is the half waveform symmetry. Almost you can think about it in the half waveform. You do this is the odd symmetry in a fundamental period. And we're going to look at this waveform in an example. And let's first look at what this will do to the Fourier coefficients. And remember, we have ft is equal to a0 plus the an times cosine n omega t plus b sub n times sine n omega t. And we have ft plus minus t over 2. We just substitute this in. And that's gonna be equal to a0 plus a sub n times cosine n omega t plus n omega plus or minus n omega t over 2, right? And then we have plus b sub n times sine n omega t plus minus n omega t over 2. And remember what the omega times t is just equal to pi, right? So therefore, these terms, the AC terms, we can rewrite ft plus minus t over 2. That's going to be equal to a0 plus the sum of a sub n times cosine n omega t plus minus n pi, right? Because omega t is equal to pi. 2 pi divided by 2 is pi. So therefore we have plus minus n pi and plus b sub n times sine n omega t plus minus n pi. Remember we had the function, let's say cosine x plus minus n pi, that's always equal negative 1 to the power n times cosine x. These trig identity, and also this is true for sine function plus minus n pi. That's going to be equal to negative 1 to the power n times sine x. So based on that, we can rewrite these equations as ft plus minus t over 2. That's going to be equal a0. And now I have negative 1 to the power nth, so I can plus the negative 1 to the power nth. I should put inside this the summation, because this summation, the n is inside. So I have negative 1 to the power nth times a0 times cosine n omega t, and plus negative 1 to the power nth times sine times bn times sine n omega t. And this is the what we have for if ft is equal negative ft plus minus t over 2. If we compare the Fourier coefficient first, the a0 is going to be equal to negative a0. So that will give us a0 should be equal to 0, right? And what about the other terms? We have the an is going to be equal, oops, so I have a sub 0 here, and there should be an. So the an should be equal negative 1 to the power nth an. And that means for the even, if n is equal, n is even, or also bn is going to be equal negative 1 to the power n times bn. And this reduces to for even n, and that means n is equal to 2, 4, 6, so on and so forth, right? And we have a0 is an is equal negative an, and bn is equal negative bn. or this will give us AN is equal to 0 and BN is equal to 0. So the property for the half-wave symmetry is we're going to have all these we have A0 going to be 0, right? And all the even harmonics going to be 0. So so the BN and AN equal 0, or A0 for these all equal 0 for N equal to 2, 4, 6, so on and so forth. Right. So this is the for the half-wave symmetry. This is the property for this waveform. Let's look at an example. Hope this example won't take too long time. Let's see. So I have a waveform here, and this plotted at this waveform has the period of 12 seconds, and we're trying to find the Fourier coefficients AN, BN, and A0s. And let's see what kind of the property we can utilize. So we can see the FT has the odd symmetry, right? Odd symmetry, since Ft is equal negative F negative T, right? That's quite clear. And also this waveform has the half-wave symmetry, because if you check any point, let's say 2, you got a 1, and you add half cycle, which is 6, you check 8, that's negative 1, and so on and so forth. You can basically fold the waveform. If you choose one period, you fold the waveform the other by 100, rotate the waveform, half of the waveform by 180 degrees, that match the other, right? So that's what this and also has half-wave symmetry, since Ft is equal negative Ft plus minus 6. 6 is a half waveform, half period, right? Half fundamental period. So based on that, we have so this one here that will eliminate all this this is the odd. So they eliminate all these A's, right? A0, AN is going to be equal to 0, and N is from 1 to infinity. And also for Bn, because now we are only left with the Bn, but the half waveform symmetry says the Bn, the even term is going to be 0. So based on this, the Bn equals 0 for N equal 2, 4. So we only need to find the Bn for the odd terms, N equal to 1, 2, 3, so on and so forth, right? And this waveform actually turns out to be even for the 3, 9, this even for the odd terms there are still zeros. Actually, this waveform is called quarter waveform symmetry. We didn't cover this in text, but we're gonna treat just as a half wave symmetry. But after the result, we will see there are additional zero terms in the Bn's we find. Okay, so let's start with the waveform. Let's just I want to copy this waveform so that I can see this. So omega equal 2 pi over t, that's pi over 6. Pi over 6. And therefore we have Bn is equal 2 over t, and we go from 0 to 12. Go from 0 to 12, and that's the Ft sine n omega t dt. And now we're going to have two intervals. I'm going to integrate in two intervals. So I'm going to 2 over t, that's 1 over 6. And the first interval is going to go from 1 to 5. Ft is, during this interval, is just 1, right? That's easier to integrate. Sine n times omega is pi over 6, so n pi over 6 t dt, and plus the other half goes from 7 to 11, and sine n pi over 6 again dt. And so the first term here is just a half over 6, and then I divide this n pi over 6 and times, and that one I'm gonna evaluate that I have become a cosine function, so I evaluate that n pi over 6 times t, value t equal to 1 to 5, and plus 1 over 6, we do the same thing, times n pi over 6, and here again, here I need to change this to the negative sign here, and that since the d cosine x is equal negative sine x dx, and I have cosine n pi over 6, and t equal to 7 to 11, I evaluate these two. And so the first one here, I got 1 over n pi, negative 1 over n pi. And inside this, the evaluation here, I have cosine 5 n pi, 6 minus cosine n pi. Because I replace t by 5, and now I replace t by 1. And this is the first term, and second term I have 1 over n pi. I have cosine 11, oh I forgot t here, 11 n pi over 6 minus cosine 7 n pi over 6, right? Too many terms, we're gonna simplify this a little bit. So let's see, first thing here is let's do two things, right? Let's see. Let's do recognize cosine 11 n pi over 6, that's equal cosine 2 n pi minus n pi over 6. Okay? Because 2 n pi is 12 n pi over 6, 12 minus 1, that's 11, right? And this one actually is going to be equal to cosine n pi over 6, because 2 pi minus x, take a cosine, is the same as cosine x. And then we use the same thing for 7 n pi over 6, and that's going to be equal cosine 2 n pi minus 5 n pi over 6, and therefore we have cosine 5 n pi over 6. So we can combine the first two terms, and if you look at the first two terms, we have cosine, actually I had an error here. I think I had an error because otherwise this becomes 0. So the error I had was this should be, because during this interval here from 7 to 11, ft is equal to -1, right? So here this should be minus, not plus. Okay, so that will fix the problem, I think. And so therefore, if we have minus here, this here should be plus, right? And I have plus here, so that will fix the problem. So therefore, the bn should be equal to 2 over n pi. I just flip these two terms inside the brackets, cosine n pi over 6 minus cosine 5 n pi over 6, right? Because this term is equal to cosine n pi, and so this term is equal 5 n pi over 6 cosine. So therefore, and I can further simplify this, because cosine 5 n pi over 6, that's actually equal to cosine n pi minus n pi over 6. So this will give me -1 to the power nth, and a cosine n pi over 6. And if we substitute this in, and we're going to have Bn. And by the way, if n is only even number, and so this is going to be equal to -1, negative cosine n pi over 6 if n is odd for n equal to 1, 3, so on and so forth, right? So because all the even term we know is 0, so we don't need to worry about that. So therefore, the Bn is going to be equal to so we double this again, right? So we have 4 over n pi times the cosine n pi over 6 for n is equal 1, 3, so on and so forth, right? So that's the Fourier coefficient we found. But also you pay attention to if n is equal to 3, and 3 over 6, that's a 2, right? That's a half of pi times the cosine, that's a 0. And so therefore, for the third harmonics also will be 0. And we just keep this form as it is now, and we're gonna go to the Python code and see what this the reconstructive waveform look like. And so this is the I'm using this the result we're having here. So 4 over n pi times the cosine n pi over 6, and we only do for the odd terms. So again, here I'm defining the original function. So if you're into the Python code, you can figure out how I define these. Basically, I use the step function, and also I take the sine function, take an absolute value, and I compare it with a constant value, and I get that the pulses, then I flip them to the other side. And so I multiply the other, based on the sine function again, and that's how I produce this blue curve. This is blue curve, exactly what we had. So we have from -5 to +5, right? And so the period is 12, and this is exactly waveform we had. And let's look at the Fourier coefficients. And how I define this is all the even harmonics for the Bn term is going to be 0, and so the modular for the modulus of the n over 2, that's 0. That means the n is an even number. I return 0. So all the Bn for the even term going to be 0 for the odd terms, and then there are 4 over n pi times the cosine n pi over 6, right? And this is reconstructed waveform. So just add the Bn, so the index here I use I, and the Bn times sine n omega t, and omega is 2 pi over t, and t is 12. So this is the waveform we reconstructed, and here we have 50 terms. And if we have a higher number of terms, let's see if we go 100, and then we should get a closer match as we did before. And let's rerun the code, and that's the reconstructed waveform. You see very close match, and we know this Fourier coefficient is definitely correct. And we utilized the properties of the two symmetries, right? Two types of symmetry. One is the odd symmetry, the other one is half wave symmetry. And okay, so that's about it for this lecture. And remember, no matter what you do, and you just need to keep going and never stop. I'll see you in the next lecture.